Today we're going to do substitution. I guess I should say, possibly next Tuesday we may go over a little more with substitution, so that's an incentive. Hopefully, the other stuff is an incentive. Should come. Before we cover substitution, there are a couple integrals I'd like to look at just briefly because they're going to come in handy, or strategy to do them will come in handy. First is the indefinite integral, if you want the antiderivative of 1 over x. All right, you want to recall what this could be. It's
natural log of x.
Did you say half the log of x?
Natural log.
Natural log, okay. Which, goes along with the fact that the derivative of the log is 1 over x. Now, if we push this a little, where a is just a constant, what happens? Well, we can start by guessing it's just going to be x plus a. And we look at the derivative of that, it's just 1 over x plus a times, because of the chain rule, the derivative of x plus a, which is 1. So here we are. We're good with that. Just going to push it a little further. We have 1 over dx plus a. Well, how can we figure that out? Well, often with finding a new integral, what you want to do is make it look like an old integral, which you know. And we can do that here if we take out this factor of 1 over b. We get 1 over x plus a over b. Well, we really know what that is, right? So we just end up with 1 over b natural log of x plus a over b. All right, now all this is building up to something really new. I want to look at x squared plus 3x plus 1. Let's keep it simple, x plus 1 at this point. Look at that and think, what do we know? Well, first of all, we can't divide this out. If that were true, x plus 1 was a divisor, then we could plug in -1 here and get 0. So -1 is 1, minus 3 plus 1 is not 0, so that's not going to work. We might also look for that, well, we could look for a pattern here, like f prime of x over f of x, but that's clearly not the case either. So we've kind of run out of steam for what we know. Well, not entirely. Everyone here should know how to divide polynomials. We've got a polynomial here of lower degree than this, so we can do long division. We will get a remainder, but we may have a problem and that we can solve. So you can pick your favorite method of division. Some of you have learned synthetic division, maybe that will work. not, we'll just do long division here. So we have x squared plus x, 2x plus 1 plus 2, 2x plus 2, minus 1. So we can convert this to the integral of x plus 2 plus minus 1 over x plus 1. Now we have something we know what to do with, right? This just becomes x squared over 2, which becomes 2x minus log of x plus 1 plus c. So, with a little creative algebra, we take something that we don't have any model for it yet, but we can break it down into something that we can handle. This technique will come in handy, and later on today we'll see it, at least one example where it's going to be used. Any questions about what I just did here? It wasn't, except for the calculus, it's kind of in algebra 2 class. Yes?
I'm just like, I don't know, it's been a long time since I've taken algebra 2. I don't really remember how to divide polynomials with long division. So
Okay.
I don't know if you could go over that one more time.
Okay, so
Yeah, it's been a long time.
don't mind spending a minute. So if I were, I'm just checking, if I were to give you something like, okay, so how would we go about this? Well, I'm honestly not trying to be condescending here. Some people just may not remember. It was a period in mathematics history, it may continue to this day, where someone decided students have to know how to divide because they have calculators. All right. So we look at 23 and we see it can go into 56 about 2 times. And then multiply. We get 107. And then we think, well, how many times can 23 go into 107? We guess. If we guess wrong, we can adjust it. Like 4, 12, 8, 92, 15, and so if you're in like 5th grade, you say remainder 15, and once you get to 6th grade, it's 24 and 15 over 23. So that's just dividing numbers. We do polynomials almost the same way, except that we have to be careful about coefficients versus our x's. We can only add and subtract things where the exponent of x is the same. So I'm going to repeat this, hopefully in slow motion here. So I'm given this problem. And I have to divide x plus 1 into this mess here. And all I really need to do is look at the leading term here, which is x, and think, well, how many times what happens when I divide x squared by x? And this could be 2, right? And then it's 2x. And then I just follow that same procedure I was using with numbers. I multiply this, this part of the, I forget the names, there's the quotient, doesn't matter. Multiply this by x plus 1. So I get 2x squared plus 2x. Draw a line, and I subtract. It's nice because this number, these numbers better match, or I'm in trouble, because I really want to get rid of the x squared here term. But this could be like 5x, and negatives are all right. So, okay, so I get 1x, right, or x plus 1. No, wait. Oh, now I do. Oh, this is going to, no remainder on this one. This is just an accident. So how many times is x going to x? It goes into 1. I multiply x plus 1. Oh, now I have no remainder. So in this case, I know x plus 1 times 2x plus 1 is this thing I started with. And here I know x plus 1 times x plus 2 times x plus 2 multiplied together and subtracting 1, I'll get this. So I've got a remainder. There is another strategy if you're reviewing and you wanted to do, you want to learn how to do this more efficiently. You have to kind of get the trick down. It only works if you have an x plus some value, and it goes like this. It's called synthetic division. And I might add, it functionally is the same as this, except you it's easier to write it down and it's easier to follow through. So it goes like this. Instead of x plus 1, I write minus 1, because minus 1 is what I add to get 0. Here I write down the coefficients. Right the first time. You have to make sure if there's missing coefficients, like if there was no 3x, you have to put a 0. Okay. First thing I do is I bring down minus 1. And I'm going to put the minus 1 here. And yeah. I didn't learn this in high school. I had to learn it as a teacher. So I'm teaching it to a calculus class. No. I'm sorry. First thing I do is I bring down the 2. That's actually not where the line goes. The line goes here. Bring down to 2. Now, nothing up my sleeve. Minus 1 times 2 is minus 2. I add. Minus 1 times minus 1 is minus 1. I add. And now I'm done. This is my remainder, which is 0. These are the coefficients, 2x plus 1 that I get up here. And this is nice if you have a big long polynomial and you're dividing by x plus or minus something. It doesn't work if you have, it doesn't work in any way I know if this is degree more than 1. So, all right. Is that enough division? William, come on up so I don't have to come back. Didn't give you your exam back, did I? There you go. Thank you. All right, so back to substitution. So first I'm going to show you what's behind it, and then we'll do a few examples to get a feel for how it's done. What's behind substitution is the chain rule. Y dx equals y du u dx. I'll use u here. This is the Leibniz notation. And here you might want to think of y as f of x and u as g of x. So that when we're using Newtonian notation, we have the derivative of this composition of functions, f and g, is the derivative of f at g times the derivative of g at x. All right. We might also look at this as f prime of u times u prime. Or, going back to the Leibniz notation, you might think of du dx, sorry. Well, you can think of du dx as the derivative of g of x. Now, I'm going to do something here which is just to show you how we get to the notation we use. This is not it's not really math. It's not a mathematical operation. Du dx equal to g prime of x. I'm going to write this as du equals g prime of x dx. Now this is useful, but one wants to be careful about trying to interpret this something. Du dx is not a fraction. Du and dx are not separate entities. And this is just, it's a notational convenience we're going to be using. So, coming back here, we have f prime, f prime g of x, g prime of x, which I described as too quickly. Integral of f of g of x prime dx is, of course, f of g of x. That's the fundamental theorem of algebra working there. So this is the integral of f prime of x, g prime of x, dx. But as I said, I'm going to call this du, and this is u. So this becomes integral of f prime of u du. Now, what's this all about? I have some integral that I'm trying to figure out. I'm trying to find its antiderivative. I make some kind of substitution here. Here we are. Some g of x. And I'm hoping that what I get is simpler and that I can compute. And how do I figure out this g of x? That's an important question. Well, the honest answer is we guess. We try and guess intelligently. We guess from experience that you don't have yet. But that's how we get there. So let's do a real example and see how this actually works. Take the integral square root of 2x plus 1 dx. You think, okay. I don't really know how to do this. We don't have a power law, or we don't have some rule that explains how we go about this. So we try and provide a substitution that will simplify it. So as a first guess, I'm going to say, why don't we let u equal 2x plus 1. Now I'm going to want to find out what this du is, and I'm going to show you the process. It's very simple to get this. I'm going to do it in 2 steps. U dx equals 2. So u equals 2 dx. Well, that's the last time I'm going to do that. You can just look at this and go, oh, my du is 2 dx. So solving for dx here, my du is 1/2. And now I can do my substitution. This becomes square root of u times 1/2 du. And sure enough, we've got an integral we can deal with here. This is 1/2 integral u to the 1/2 du. It's 1/2 u to the 3/2 over 3/2, or times 2/3. Let's see. 2's cancel, and we get u to the 3/2 over 3 plus c. Now, when we're doing an indefinite integral like this, well, that's all fine and good, but we really don't care about u. We care about is x. That's fine, because we know what the relationship between u and x is. So we just end up with 2x plus 1 to the 3/2 over 3 plus c. So that's the process. We look at this, we try and think of a substitution, yes, that might simplify this, and then we go through this process and see if it works, see if it helps. Now, you might think that you have to guess really carefully. And it's certainly the case that before you're done, you'll make some guess and it won't work. However, it's not the case that only one substitution is possible. I'm going to demonstrate that. We're going to try this again. And this time we'll try say u squared equals 2x plus 1. Well, why would I do that? Well, that not only gets rid of the 2x complication, but it gets rid of the square root too. Okay. How's that going to work? Well, u equals the square root of 2x plus 1. So du equals, okay, I have to find the derivative of this. It's just to the 1/2, so 1 over 2 square root of 2x plus 1 times 2, right? This is a chain rule. So this just ends up 1 over the square root of 2x plus 1 du. Right? Now let me do my substitution. This just becomes u. This is dx. Well, I have to solve for dx here. That's going to be square root of 2x plus 1. What I wanted to do? I think that's what I wanted to do. Well, this is just u. So what do I end up with here? I'm just going to write it all out. So 2x plus 1 becomes u squared. Dx becomes u du. This just becomes the integral of u squared du, which of course becomes u cubed over 3 plus c. Well, again, we have to substitute back. So we substitute u back in here, and we get square root of 2x plus 1 cubed over 3, which is just as we had before, 2x plus 1 to the 3 halves over 3. So different substitutions, one of them might not work, but if they both work, you'll get the same result. Let's try a different problem. This is, it looks similar, it has a similar challenge to it, but it's not all that different. 1 plus 1 over 1 plus the square root of x. Okay. Any thoughts on what my substitution should be? Again, we're just guessing. How can I? What's the problem here? We don't know what to do with that. We see things like that. 1 plus x, or 1 over 1 plus x squared. We can handle these, right? Sure.
You substitute square root of x as u.
Yeah, that sounds like a good, especially when you get started, you're never going to know for sure, but that sounds like a good place to start. I'm going to, because it'll be easier further up, I'm going to call this x to the 1/2. All right, so my du, this is kind of the mechanical part. Well, it's x to the 1/2, negative 1/2 dx. So dx is equal to what? Is that right? I think I'm doing it the hard way, but that's all right. All right, I could do it the hard way, but I'm gonna make this simpler. This is u squared equals x, right? So the derivative of u squared is 2u du, and this is just dx. That's going to make life easier. Right, so my integral becomes what? 1 over 1 plus u, and dx becomes 2u du. Right? Well, at first glance, this doesn't seem to have helped any because, again, we haven't seen what to do with this. We don't have some, it's not like the secant or something, inverse secant or something like that. It doesn't fit that pattern of f prime over f. But recall at the beginning of class, we talked about simplifying this by dividing. Let's give it a try. 2u over, I'm going to write this u plus 1, was in 2 times. 2u plus 2, this is 0 here, so we have minus 2. So that means this is the integral of 2 minus 2 over 1 plus u. Well, it's kind of like magic. We know what to do with that. It's just 2x minus, well, 2 times 1 over 1 plus u is the log of 1 plus u. I'm sorry, this is not an x, this is a u. So now all we have to do is go back and substitute in, right? So it's 2 times the square root of x times 2 times the log of 1 plus 1 over the square root of x. Now, when you're doing these, especially the first time, you might think, well, how do I know that's the right answer? And of course, the solution to that problem is you do something that you know how to do well. You find its derivative. So, okay, 2 times the square root of x is the derivative. It's 2 times 1/2 times x to the 3/2. I think I got that right. Divided by 3/2. Wait a minute. minus 2 times 1 over 1 plus the square root of x. That use the chain rule, 3 over 1 plus the square root of x is what? 1/2 x 3/2 plus 0. Right? These cancel. These cancel, so I have x to the 3/2 plus x to the 3/2 over 1 plus square root of x. I feel like this isn't coming out right. Well, keep going. When I take out square root of x, I get 1 plus 1 over 1 plus square root of x. So that's what? 1 plus square root of x plus 1 plus square root of x. Square root of x minus 2 plus the square root of x over 1 plus square root of x. I definitely did something wrong here. I've done wrong. Well, that's bad. Tell you what, why don't you take a break? I'll try and figure out where I went wrong, and we'll fix it when we come back, all right? Well, that was damn frustrating. All right, let me just a second.
And you're trying to get rid of
All right, I guess
you're trying to get rid of this, right?
the lesson for me is it's best to do math in a small room with no one around where it's perfectly quiet and you don't make really stupid mistakes. That's the right answer. Just when I started finding the derivative of square root of x, I kept coming up with the wrong answer.
That's to the power.
Derivative of the square root of x is 1 over 2 times the square root of x. So 2 times it is just 1 over it. Log is just 1 over 1 plus square root of x. And the derivative of the square root of x, here it did. These two cancel. And this doesn't look right at first, but if you take out square root of x, put it over common denominator, you end up with square root of x over 1 plus square root of x. These cancel and you get what you wanted. Yeah. there's another lesson there too. Is sometimes you do a problem and you check and it doesn't check and you did the problem right. Check this wrong. There are going to be some homework problems, and you should practice them with them. You should beat your head up, trying to get the right answer. You can always check it by finding the derivative. All right. I want to show you another kind of substitution that takes a little more forward thinking. Okay, x over square root of 1 minus 4 x squared. So you look at that, think, where have I seen that before? Well, I've seen this before, haven't I? Anyone remember where this comes from? The derivative of something. That we've seen.
Inverse sine.
Inverse sine, right. Well, okay. How does that help you? Well, first of all, it's not x squared, right? But I made this 2x. And what would happen? This would become 4, but I'd have to multiply by the derivative of 2x, right? Chain rule. So if I started off with 1/2, that would go away. Again, that would, but there's still an x here. It's not exactly obvious what to do here. However, this construction here, 1 minus the square of something, right, that's really 1 minus 2x squared. That should make you think of the Pythagorean identity. How's that going to work? Oh, I could plug in a sine or a cosine here, but that doesn't really work, does it? But I could put in, you can look at it this way. Well, that's 4. Well, that doesn't work either. Well, let's just kind of shoot the moon here. What if I said x equals, what did I try? On page. If I did try sine of u over 2. Okay, so dx equals cosine of u over 2 du. Oh. Well, that has possibilities. Okay. this becomes sine of u over square root of, sorry, sine of u over 2. This becomes 1 minus 2 sine of u over 2 squared. And dx becomes cosine of u. Okay, let's do a little simplifying here. Take that, well, leave that in there for a moment. Sine of u over 2. What does this become? This becomes 1 minus sine squared. So the cosine squared, we're finding the square root of it. What's the cosine of u times cosine of u over 2? So I can take out a quarter, 2 halves. Sine of u. It's starting to look like it could work. Right? So that's 1/4. Well, it's the integral, it's the antiderivative of the sine. Should probably know that by now. Find it on the internet.
Negative
about-
cosine?
Is that Lillian? No, sounded like, oh, okay. Stop impersonating Lillian, please. Negative cosine. Let's see. All right, well, what did u equal? Oh, wait a minute. Now we have a problem here. We can't just plug u in, can we? We have x equals sine of u over 2. We don't want sine of u, we want cosine of u. Anyone have any ideas how we might? I guess that pre-calculus identity stuff is far away. Well, let's see if we can get this, make this into a cosine. Right? X equals the sine of u. We square both sides. And we're going to subtract both sides from 1. Now my Pythagorean identity works for me. Sine squared plus cosine squared is 1. 1 minus sine squared is cosine squared. But I just have one cosine, not cosine squared, so I have to find the square root of it. So I get negative 1/4 square root of 1 minus 4 x squared plus c. All the way back here. So, this is kind of odd because the sines and cosines are useful for finding this, but they're not in the integral and they're not in the result either, are they? Kind of a nice, pretty result. All right. there's one more piece to this puzzle. Everything we've been doing here has all been indefinite integrals, and just finding the antiderivative. I'm going to go back to that first problem we did. It was pretty simple. Went like this. What's the integral of the square root of 2x plus 1? And we decided that was 2x plus 1 to the 3/2 over 3 plus c. So if I make that a definite integral, by now you should know that this is 2x plus 1, 3/2 over 3, evaluated between 1 and 4. All right, we might as well go through it. So 8 plus 1 is 9. Square root of 9 is 3. 3 cubed is 27 over 3. Minus, okay. 2 plus 1 is 3. Cubed is 27. Square root of 27 over 3. We can simplify. This is 9. And since 27 is 3 times 3 times 3, this is just square root of 3. All right. But there's another way to get there. And it involves the substitution rule for integrals, for definite integrals, which looks like this. Definite integral from a to b, f prime g of x times g prime of x dx, given that u is equal to g of x, is equal to the integral from, we'll get to that part, f prime of u du. Now we have to change the limits. Well, we change the limits to g of a and g of b. Right, so how did we get from here to here? We said that g of x is what? 2x plus 1. Is that how we did it? Go back and see. Yeah, that's how we did it. So g of 4 is what? 9. And cube 1 is 3. So this is going to be, now we have to do this problem again. This turned out to be 1/3 cubed to the 3/2. But now it's from 9. Right? Square root of 9 is 3. Cube 27 divided by 3 is 27. Three cubed is 27. Square root of 27. Square root of 27 over 3 is square root of 3. So it turns out the same if you use this formula. You can kind of forget about this if you want. If you can find the integral, you can just evaluate it over its original limits. Sometimes this might be more convenient. That's all. Yes.
Wait, are they the same? Are they the same?
Well, first of all, nobody caught me when I made that math error. Square root of 9 is square root of 9 is. Did I do this wrong? Yeah. Square root of 9 is 3. 3 cubed is 27. 27 over 3 is 9. That's what I said. I just wrote down the wrong thing. Is that okay? So if there's anything else I want to say about this. All right, I think we're going to just do one more example because it looks scary, but that's the moment when you're doing integrals where you have to kind of buckle up and think, well, it can't be that bad. All right, so we have to think of what we could do. What could we do to simplify this? And what's the part of this we really are thrown with? We don't really have any idea the integral of the log of x is, do we? You know what its derivative is. Try that. Set u equal to the log of x. So we're finding the derivatives. We get du is what? 1 over x dx. Well, a lot of times you're going to get a nice, happy result having from that, because clearly what we have here is the integral. This is my g of x, and this is my, f of g of x, f prime of g of x, and this is my g prime of x down here, right? So, all right, let's substitute. Log of x becomes u. 1 over x dx becomes du. And this integral is trivial, right? This is just u squared over 2 plus c. Well, that would mean that the answer we're looking for is log of x squared over 2 plus c. So, serendipitous result. guess before we go, we should check that one, see if I can do that confidently still. So what's the derivative? What's the derivative of log of x squared over 2? Well, this is just the basic chain rule. 2 times log of x over 2 times the derivative of the log of x, which is 1 over x. So it's just what we wanted, log of x over x. Just like magic. Okay, well that's really it for the, the hard part of this class. We'll look back at this on, next Tuesday.